Okay. Okay. So again, I give a quick description here that we are having a problem in which there is a air preheater in the form of bundle of tube across which the flue gas is flowing. The temperature on the left hand side where the flue gas starts moving across the bundle of the tube is T1, that is equals to 250 degrees Celsius. Outlet temperature we don't know. As the flue gas move across the bundle of the tube, it get cooled down because each of these tube the air is flowing through each of these tube with a temperature of 120 degrees Celsius, and therefore some of the heat is taken by the air which is flowing through each of these tube, and therefore the flue gas temperature decreases as it moves across the bundle of the tube from left hand side to right hand side. Again, what is been given in this problem is transverse pitch is given. So transverse pitch is given as 25 2.5 centimeter, so that becomes 0.025 meter. Longitudinal pitch is given as 0.03 meter. The diameter of each of these tube is given as 1 inch outer diameter, so that becomes 0.0254 meter. Velocity on the left hand side is given as 5 meter per second, and the arrangement given here is a staggered arrangement. Now what we have to find out is we have to find out the outer temperature first, and based on that we have to find out, calculate the drop in the flue gas temperature. That is what the part A is. So we have to find out how much temperature drop is going to be there from the actual temperature of T1 equals to 250 degrees Celsius. That is the first part. And in part B, what we have to find out is the rate of heat transfer to the air. So how much is the rate of heat transfer from the flue gas to the air which is flowing through each of these tubes, that we have to find out. Again, what is been given is there are 10 such transverse rows are there. So 1, 2, 3 in such manner there is a 10 transverse rows are there, and in each row there are 12 tubes are there. So that means the total number of tubes are 120. So total number of tubes are 120. How? So each of these row is going to be what? This is 1, 2, 3, and that goes all the way to 12. And similarly with another color, let me just take another color here. So this 2, 3, and that all the way goes to 10. So there are 10 transverse rows and there are 12 tubes in each row. So if I'm taking a one row, so one row is basically what? This comprises of these tubes which is there in a zigzag order. Okay, clear? Okay, so now in this particular problem, the properties of the flue gas is given at 250 degrees Celsius. So that is rho is given as 0.666 kg per meter cube. Mu is given as 2.8 10 raised to power minus 5 kg per ms. Thermal conductivity is given as 0.042 watt per meter degree Celsius. Prandtl number is 0.683 and Cp is 1035. Again, one more thing to note down here is in a normal circumstances, whenever we are solving a forced convection problem, in general, the average temperature has to be used between the two extreme ends. So two extreme ends are what? T1 and T2. So between T1 and T2, we have to take the average temperature. So that is for the forced convection. When we are taking at the free convection or a natural convection, that you will see later on in the next tutorial. In the natural convection case, the average temperature is always between the temperature of the free stream and the temperature of the wall of the surface. So in this case, wall of the surface is a post convection, and therefore the average temperature has to be between T1 and T2. Okay, so this is a very important point to note down. Mostly people make mistake here. Okay, So now, since we don't know the average temperature, we don't know the outlet temperature T2, we don't know the average temperature here. So we can start the calculation with the basis that the average temperature is just 250 degrees Celsius. That means the outlet temperature is 250. So assumption here is, so the first assumption which we are going to make in order to solve this particular problem is, assumption. So this is iteration 1. So we will start with the assumption that T2 is same as 250 degrees Celsius. Okay. So this is only for calculating the properties. That's it. So this temperature we are using only for calculating the properties, because we have to calculate the properties at average temperature. So if we consider T2 equals to 250, that means the properties at the average temperature are going to be the same as whatever is been given in the problem statement here. Okay. So with this we are going to solve this problem and we will find out the new value of T2. If this new value of T2 is same as 250, then nothing is required, isn't it? If it is not same, in that case we will go for the next iteration, and in the next iteration the average temperature we are going to find out based on the outlet temperature we have found out in the previous iteration, plus 250 divided by 2. Okay. So now in this case we start with the 250 degrees Celsius itself. Okay. So now this is a staggered arrangement. So what we have to first find out is SD. SD is nothing but the diagonal pitch. So before we start, let me open the presentation so that you will be able to appreciate what we are doing and why we are doing. So let me just open that and give you a background, and then we will start solving it. Okay. So can you see the presentation, PowerPoint presentation? Hello? Is it visible?
Yes, sir.
So let us look at, so this is what the case is. This is what the staggered case we are looking at. Now how we solve this problem? The first thing what we have to do is, for solving this particular problem, what we have to do is, the Nusselt number is given in terms of the Reynolds number and Prandtl number. Again, the Reynolds number and the Nusselt number, these are defined in terms of the diameter of the tube. Here D is nothing but the diameter of the tube, and Reynolds number here is based on the maximum velocity, where maximum velocity Vmax is calculated based on ST, SD, D and V, isn't it? So SD we don't know. So SD we have to calculate first. From that we will calculate Vmax. From Vmax we will again the staggered arrangement is there, so we will find out ST by SL. We will put this Vmax in this equation. We will find out the Reynolds number, and depending on the Reynolds number and ST and SL ratio, we are going to select the value of C and M. That we are going to put it in this equation and then find out the Nusselt number, and then thereafter we are going to find out the transfer coefficient. Okay, so this is what we are going to go ahead with, correct? So let me just go back to our whiteboard. Okay, so I have to first find out SD. So now SD is what diagonal pitch is directly given as SL square plus 1 by 4 ST square, and if we put the values, this comes out to be SL is the SL value in this case is 0.03 square, and 1 by 4 SM is into 0.025 square. So this comes out to be, what is the value of SD? It is going to come as 0.0325 meter. Okay. Now from where this equation is coming? This equation is directly coming by looking at the geometry itself. Remember here, between these two tubes, the distance is ST, and the SD is nothing but this particular distance. So half of this ST, so square of that is going to be 1/4 ST square, isn't it? Plus SL square. So that is going to give me the SD square. So therefore SD will be given as under root of SL square plus 1/4 ST square. Is it all right? Are you all able to get it? Hello? Hello?
Yes, sir, it's clear. Yeah.
It's clear? Okay. Perfectly all right. So now based on the SD, now we can calculate Vmax. That is nothing but the maximum velocity which we are going to have, because there are restrictions are there. So the area for the flow is going to decrease as we move across the bundle of the tube, and therefore the velocity is given as Vmax. So that is defined as, for this staggered case, it is defined as 2SD minus D into V. So this is what the equation is. ST we already know, that is 0.025 divided by 2. SD we have calculated, that is 0.0325 minus diameter is 0.0254, diameter of each tube, multiplied by 5, that is the velocity given. So Vmax comes out to be, so Vmax comes out to be 8.803 meter per second. Is it clear to everyone? Hello? So now based on this Vmax, we have to find out the Reynolds number, because our ultimately aim is what? If I go back to this particular figure, what is my aim? My aim is to calculate this T2. How I can find out this T2? I can, find out what is the total heat transfer taking place between the flue gas and the air flowing through each of these tubes. That can be done easily by the heat balance. So in this case, the total amount of heat transfer can be directly given as HA delta T LMTD. Why LMTD? Because as I move across from left hand side to right hand side, my temperature difference is varying. So at this end, my temperature difference is what? 250 minus 120. Remember, the heat is being transferred to the fluid which is flowing through each of these tubes. So that means delta T at this end is going to be what? 250 minus 120. But as I move across this bank of the tube, at this end on the right hand side, the temperature difference is going to be what? T2 minus 120. And this temperature difference is going to be lower than the temperature difference which I am going to have at this particular end. So clearly the temperature difference is varying as we move across the length here bank of the tube, and therefore one has to use log mean temperature difference. So the heat transfer in this case will be given as HA delta T LMTD, and that should be same as the amount of heat that being transferred by the hot fluid to the cold fluid, isn't it? So amount of heat transferred by hot fluid to cold fluid can be given as how much the sensible heat given by the flue gas. So that means what? MCP dt. Only MCP dt. So we can directly find out T2. Only unknown that equation you will have is a T2. So that is what we are trying to do. Okay. But as you can see, in order to find out the total amount of heat transfer, one need to find out the heat transfer coefficient. And therefore, what we have to do is, first we have to find out the Reynolds number based on this. And once we know the Reynolds number, then we can use the correlation and find out the heat transfer coefficient. Okay. So Reynolds number RED max, I can directly write down here as RED max is nothing but dV V max rho by mu. So all the values are already given. So D is 0.0254, V max we have already calculated, that is 8.803. Rho at 250 degrees Celsius, which is given as 0.666, that is already given in the problem statement itself. So I will just write down the values. Rho is given as 0.666 kg per meter cube. Mu as 2.8 kg per meter second. Thermal conductivity is given as 0.042 watt per meter degree Celsius, and Prandtl number is given as 0.683. So we can put all these values in this equation. So mu is 2.8 into 10 raised to power minus 5. The Reynolds number which we are going to get it. Please calculate. Calculate the Reynolds number. Anybody? So anybody got the value of Reynolds number? It seems to me like all other are, not at all, solving the problem. It is only.
Sir, 5.318
into 10 to
Okay.
power.
Good. I am
2.
happy that some students are solving. I do have the answers, but I want you guys to solve. See, every year I solve these problems. So if I solve it one more time, it doesn't, going to add anything in my knowledge. But of course, this is for you to understand, isn't it? So please solve the tutorial questions along with me. Don't sit idle. So this should be around 5320. Is it correct? Hello?
Yes, sir.
Yes, sir.
So now we have to select the correlation. So let us first find out ST by SL. So ST by SL, if we calculate, that is 0.025 divided by 0.03. So definitely that is less than 2. So we can look at the table. From table, we can calculate the constant C. So constant C is given as 0.35. 0.025 divided by 0.03 raised to the power 0.2. So this comes around 0.337, and the M obtained as 0.6. So based on this, now the correlation one has to use is this. So Nusselt number NUD is CRE raised to the power M, Prandtl number raised to the power 0.36, and and one more thing is there, so that is PR by PRW raised to the power 0.25. Okay, this is what the correlation is. So as given in the problem, again we can assume that there is no viscosity changing as we move from the wall, so we can assume this equals to just 1. So what we left with based on this is Nusselt number in terms of the diameter of tube is given as 0.337. Reynolds number is we have already obtained 5320 raised to the power M, so that is 0.6 into Prandtl number is 0.683 raised to the power 0.36 into 1. So what we obtained from here is, please calculate. Hello. So this should come around 50.5. Check whether this is correct.
Yes, sir.
Yes, sir. 50.53.
So this is given as HD by K. We already know the diameter of the tube, that is 0.0254. Thermal conductivity also we know. So we can find out what is the value of H. So H can be obtained as 50.5 into K by D. So that is 50.5 into K. In this case is 0.042 divided by D is 0.0254. So this comes out to be 83.6 watt per meter square degree Celsius. So this is what we are expected to get. Check whether this is correct. Is it correct?
Yes, sir.
Now, in this case, as I said in the starting itself, we have to make the balance. So balance in this case is what? Balance is the amount of heat transferred should be same as the amount of heat lost by the flue gas, isn't it? So balance in this case is amount of heat transfer. Maybe I just write down amount of heat transferred is amount of heat lost by amount of heat lost by flue gas, Okay, so amount of heat transferred we can directly write in terms of what? Amount of heat transfer is HA delta T LMTD. That is going to be the amount of heat transferred. Amount of heat lost by the flue gas will be given by what? MCP delta T. Isn't it? MCP delta T. Now in this particular balance, this M we don't know. This M we don't know right now, we don't know, but we can calculate because the velocity is given. We can find out what is the cross sectional area for the flow, and based on that cross sectional area into velocity is going to give me volumetric flow rate. Volumetric flow rate multiplied by density is going to give me mass flow rate. And the mass flow rate we can multiply here and we can find out how much is the heat lost by the flue gas, isn't it? So let us find out the area of the cross section for the flow. So area cross sectional area, just wait. Cross sectional area for flow. Okay. So now what will be the cross sectional area for the flow? Let me just go back to the figure again. Okay. So the cross sectional area, just wait. Okay. So cross sectional area is going to be what? Cross sectional area is going to be this area. Remember, so this height we can find out because the transverse pitch we know, and we know how many rows are there, and also the width in a z direction. So that means the length of the each tube we know. So length of the each tube is 1 meter. That is what is been given. So we can easily find out the cross sectional area for the flow. So here there are 10 transverse rows are there, 1, 2, 3, there are 10. And again you can see when we are saying 10, so some area is here top because it's a zigzag arrangement. So it's not 9 into 9 into ST is not the height. In this case, it is going to be 10 into ST. Why? Because this is a zigzag arrangement. So at the end, we will have one more tube at the bottom here, and also some space will be left here at the top. Little bit space similar to this will be left here. So that becomes 10 into ST instead of just taking 9 into ST. Okay. So that we have to carefully see here. Is it all right? Are you all able to get it? What I'm
Sir,
trying to
if
say?
the arrangement had not been staggered, then we would have taken 9 rows, right?
In that case also we would have taken 10 rows because see above the top there will be some space will also be available for the flow, isn't it? It's not just that we are restricting the flow exactly at this boundary.
Right. Okay.
Isn't it? In that case also it is going to be 10. So are you all able to get it what I'm trying to say here? Okay, so area for the flow in this case is going to be what? 10. So that is 10 is the transverse rows are there. That is what is been given in the problem statement. Into what is the pitch of the transverse? Transverse pitch is given as ST is given as 0.025 into the length of each tube in a Z direction, so that is 1 meter. So this is going to be the area for the cross-sectional area for the flow. So that is so this is going to be 0.25 meter square, correct? Now what will be the volumetric flow rate? Volumetric flow rate is going to be 0.25. So that is area into velocity. Into velocity is 5. So that becomes 1.25 meter cube per second, isn't it? And mass flow rate in this case is going to be what? Volumetric flow rate into density. So that becomes 1.25 into density. Density is given as 0.666. So this becomes 0.832 kg per second. Okay, now let us make this balance. Now H we have already calculated, isn't it? So H is, if I go back at the top, H we have already calculated. So H is 83.6, isn't it? So I am just making the balance again here. So 83.6 into area. What will be the area? Now this area is area for the heat transfer. This area for the heat transfer and this AC are not same. AH is the area for heat transfer. So area for the heat transfer is going to be what? Area for the heat transfer for one tube is pi dl. And how many such tubes are there for heat transfer? There are 120 tubes, isn't it? So 120 multiplied by pi dl, that is going to give me the total heat transfer area for all the tubes. I can go back again at the top to explain you what I'm trying to say here is area for the heat transfer is the area around this tube, area around all these tubes, isn't it? That is the area for heat transfer. Area for the flow is only this area which is going top as well as in the Z direction here. So this area is nothing but the area for the flow, whereas okay. So now okay. So now let us look at the balance again. Let us go back to our balance one more time. Okay, so 83.6 into area of one tube is going to be pi dl. So that is pi into d is 0.0254. Length of one tube is 1 meter and there are 120 such tubes, so that 120. So this is the area for the heat transfer into delta T LMTD. What is delta T LMTD now? The temperature difference at the left hand side of this particular figure is, so temperature difference here is 250 minus 120 and temperature difference on the other side is a T2 minus 120, and based on that we have to find out the log mean temperature difference. Okay, so we can calculate this as ln, sorry. So this becomes 250 minus 120, that is the first temperature difference, minus T2 minus 120 divided by ln 250 minus 120 divided by T2 minus 120. So this is the log mean temperature difference. This is the log mean temperature difference, and this should be equals to mCp dt, isn't it? This should be equals to mCp dt. So m we have already calculated, so that is 0.832. Specific heat of the flue gas is given. So specific heat of the flue gas at 250 degrees Celsius is 1035, and delta T in this case is going to be what? 250 minus T2. Isn't it? Correct. So this is what the balance is going to be. Now this particular factor and this factor is going to get out. So this is 250 minus T2. So this 250 minus T2 on the right hand side and the left hand side is going to get cancel out. And if you rearrange this n, so this is 250 minus 120 is going to be 130 divided by T2 minus 120, and by calculating everything, what we are going to get on the right hand side is 0.929. 0.929. That is what we are expected to get. Check whether this is correct. And if we rearrange this, what we are going to get is T2 comes out to be 171 degrees Celsius. Just check whether this is correct.
Sir, earlier in this question, you were talking something about the first iteration and how we are taking T2
So
to be 250.
we are going to look at the second iteration also. Just wait.
Acha, okay.
We are not end here. There is one more iteration we have to perform. Okay. So just check whether these calculations are correct or not. Okay.
Yes, sir, these are correct.
Okay. So now the outlet temperature which we have obtained is 171. But remember what outlet temperature we have started with? We started with 120. Isn't it? If I go back here at the top, remember we started with we started with 250. So that means the assumption of average temperature of 250 degrees Celsius is not, isn't it? It's not correct. So that means what we have to do is we have to find out the new average temperature, find out the properties at that new average temperature and do this entire calculation again. And this iteration has to be continued till we get the assumed value of average temperature which is used, assumed value of outlet temperature which is used for calculating the average temperature, and the actual outlet temperature which we have obtained at the end. These are same. So we have to continue the iteration in such a manner. Okay, till these two things become same. Okay, so now let us go to the next iteration. So iteration number 2. So in iteration number 2, first we have to find out the average temperature. Average temperature in this case is going to be what? 250 plus 171 divided by 2. So this comes out to be 210.5 degrees Celsius. Correct? Isn't it? Is it correct? $210 by 5. Okay, so now we have to find out all the properties at this temperature. Remember, we have taken the properties in earlier iteration at 250 degrees Celsius, which is not correct because we have to take all the properties at average temperature. So that calculation itself was based on the assumption that the average temperature is 250 degrees Celsius, but that is not the case. The average temperature comes out to be 210 in this case. Now find out the properties. So properties are already given in the problem statement itself. So the properties at 210.5 are rho is given as 0.72 kg per meter cube. Mu is given as 2.48 into 10 raised to power minus 5 kg per meter second. K is given as 0.04 watt per meter degree Celsius, and Cp is given as 1030 joule per kg per degree Celsius, and Prandtl number is given as 0.683. So these are the new properties at this particular temperature. Now we have to repeat all the calculations again. Okay, so Again, in order to repeat the calculation one more time, we have to first find out the maximum velocity, then the Reynolds number, and then based on that we have to select the correlation, isn't it? So now in this particular case, remember, even the velocity which we have used, the velocity of 5 meter per second that we have used, that is at that particular temperature. So now in this case, again, as the average temperature is different, that velocity is going to be changed. That is not going to be the same. Why that is not going to be same? Because that is the velocity which we have assumed at the average temperature of 250. But now the average temperature is reduced to 210.5, and therefore the velocity is also going to decrease accordingly as per the ideal gas law. So here what we are assuming that the velocity is changing, but mass flow rate is kept constant. Mass flow rate is kept constant. Make a balance here. So mass flow rate is constant. So mass flow rate, if I keep it constant, mass flow rate, if I keep it constant, so mass flow rate is nothing but what? Rho into volumetric flow rate, isn't it? Rho into volumetric flow rate. So now this mass flow rate can be as this rho is m by RT. So this is given m is given as if you use the ideal gas law, basically what you are going to get here is V1 by T1. V1, this is mass flow rate, isn't it? So maybe I'll just do it separately. Okay. So this is mass flow rate. So basically rho is given as Pm by RT into V dot. So these are the volumetric flow rate. So for two cases, M P RT1 V1 dot should be as MP RT2 V2 dot. These dots are nothing but volumetric flow rate, and this is mass. This is mass. Sorry, this is not mass flow rate. Mass flow rate is only this. Okay, so if we rearrange this, basically what we get is V dot T1 should be same as V dot T1 should be same as V2 dot T2, and V1 is mass flow rate. So that means what? Area into velocity, isn't it? So that is nothing but area is constant. So this is nothing but just the velocity V1 by T1 should be same as V2 by T2. Okay. So we can accordingly find out the new velocity for a new temperature based on this. This is just the extension from the ideal gas law. We are assuming here that the mass flow rate is kept constant. Okay. So now based on this, my new velocity V is going to be what? My new velocity is going to be in this case we can directly obtain that as 5 into 468.15 divided by 523. Maybe I just wait, and what 273 divided 250 plus 273. So this is going to give me the new velocity at the new average temperature. So this comes out to be 4.62 meter per second. Now based on this I can find out V max Vmax in this case can be obtained as again ST divided by 2SD minus D into V. So this is nothing but 0.025 divided by 2 divided by 0.0325 minus 0.0254, and the numerator is multiplied by 4.62. So this comes out to be, Vmax comes out to be 8.13 meter per second. Just check whether these calculations are correct. Is it correct? Is it correct? So this is nothing but okay. Is it correct, everybody? Hello? 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 Is it correct? Can we go ahead? Okay. So now based on this, now once we know the Vmax, then we can calculate the Reynolds number, new Reynolds number. RED max in this case is going to be dV max by rho by mu. So we can put the new values here. So 0.0254 is the diameter, 8.13 is going to be the velocity. Rho, the new density value which is given at the 210.5 degrees Celsius. So that value is 0.72 divided by mu, and mu is in this case is 2.48 into 10 raised to power minus 5. So this comes out to be around 6,000. This comes around 6,000. Okay, is it correct? So now based on this we can find out the Nusselt number. Nusselt number is, again we can use the same correlation, that is 0.337 Reynolds number raised to the power 0.6 into Prandtl number raised to the power 0.36, and the another part is factor is PR by PRW. So PR by PRW, so PR by PRW raised to the power 0.25. So we can put all the values in this equation and we can solve this particular problem. So this becomes 0.337 into 6,000 raised to the power 0.6. Prandtl number is already given as 0.683 raised to the power 0.36 into just 1. So this comes around to be 54.3, and this is nothing but HD by K. So we can find out the new value of heat transfer coefficient, and the new value of heat transfer coefficient in this case comes out to be 54.3 into K. The new value of K is 0.04 divided by 0.0254. So H comes out to be 85.5 watt per meter square degree Celsius. So this is the new value of heat transfer coefficient. Now based on this heat transfer coefficient, again make the balance just to check what exit temperature we are getting. So again making the balance. So balance in this case is same. MCP delta T is given as HA delta T LMTD. So this is what we are going to make it again. So M we already know, since mass flow rate is going to remain the constant. So that is just 832. It is not going to change. CP value is 1030 into delta T in this case is going to be 250 minus T2, and that is given as H is 85.5 into area is going to be pi dl into 120. So pi into 0.0254 into length is 1 meter into 120 tubes are there. So this is 120 and multiplied by delta T LMTD. So that becomes 250 minus 120 minus T2 minus 120 divided by ln 250 minus 120 divided by T2 minus 120, and this entire thing is in the bracket. Okay, so from this balance, this numerator of this get cancel out with this. Again, if we simplify further the equation, what we expected to get here is ln 130 divided by T2 minus 120. So that comes out to be let me just calculate it. So it becomes 0.832 into 1030 inverse multiplied by 85.5 into 3.14 into 0.0254 into 120. So this becomes 0.9548, and from this T2 can be obtained as so exponential of this inverse into 130 plus 120. So this comes out to be 170.03. So clearly the outlet temperature is coming as 170, and since the outlet temperature we have assumed in calculating the average temperature is same as 170, that means we don't require the additional iteration here. Since the outlet temperature is same as the assumed outlet temperature, for calculating the average temperature, no more iterations are required. No more iterations are required. Okay. So clearly this is the outlet temperature. So based on this, now we can find out the answer of part A. So part A is the drop in temperature. So drop in temperature that can be obtained as 250 minus 170 degrees Celsius. So that comes around the drop is 80 degrees Celsius. Part B, we have to find out the heat transferred, the rate of heat transfer to the air, the rate of heat transfer to the air, rate of heat transfer to the air is given as, in this case, is given as mcp dt. So that is 0. mcp delta t. So this we can directly obtain 0.832 into 1030 into 250 minus 170. So this comes around 4 6 8 560 watt. So 68.56 kilowatt. So this is the answer for part B. This is the answer for part B. Okay. So are you all able to get it? What we are doing? Hello? Hello?
Yes, sir. It's fine. Yeah.
Okay, so we will stop here, but I have one more request. I think so many students are not attending class out of 100 students I was expecting, isn't it? So can we shift this tutorial directly on Monday itself? So we will have only one tutorial class on Monday. So anyway, it is going to get recorded, isn't it? That is what the students are doing. They are not directly attending and they are looking at only the recordings. What do you say?
Yes, sir, it's fine.
So we will discuss in the next class. Probably then we will have only one tutorial directly on Monday, isn't it? So all 250 students can join on Monday. Anyway, not all the students are joining, isn't it? Not even Monday batch and not even in the Tuesday batch. So is there any time clash for you?
No, sir, there is not.
So then there is no point in having the tutorial on separate tutorial class on Tuesday. So probably we will have only one tutorial class on Monday, isn't it? So that's going to save a lot of time for me, if that is okay from the student side.
Yes, sir, we don't have any problem.
Okay, so we stop here. Anyway, we will discuss this in the next class, and based on that we will go ahead. Okay, so see you then on Thursday class. Okay.